Okay, come, let's go on to section 3 on ionic bonding. Okay, now you know that ionic bonds are formed when you have valence electron transferred. So we are talking about transfer of electrons. So when electrons are transferred, you actually form cations and anions. So the attraction between the cation and anion, this will be known as the ionic bond. Okay, so what do we define as ionic bond? The ionic bond is the electrostatic attraction that is between the oppositely charged ions. Okay, now take note that ionic bonds, they are usually formed between reactive metals, which are your group 1 and group 2, as well as non-metals. So in other words, we are talking about atoms with large electronegativity differences. Okay, now generally, your group 14 elements, they will not take part in ionic bonding because you realize that in order to lose or gain electron, you require a lot of energy. So therefore, group 14 elements, they usually do not have ionic bonding. Okay, so let's take a look at dot and cross diagram for ionic bonds. Now, if we look at sodium chloride, okay, now I know that you have done dot and cross diagram before in secondary school, all right? But take note that at JC, at A levels, when we draw dot and cross diagram, we only represent the valence electron. So if you look at sodium, the electronic configuration for sodium is 1s2, 2s2, 2p6, 3s1, right? So this is the valence electron. 3s1 is the valence electron. So therefore, we will only show one valence electron on sodium. All right. Whereas for Cl, there are 7 valence electron. So if there are 7 valence electron, we represent the electron on, chloride. So we will represent the 7 valence electrons on chlorine atom as crossed. Okay. So what happened here is one of the electron, your sodium valence electron, one electron on sodium, the valence electron will be transferred to Cl. So forming your Na plus. Now Na plus, there is no more electron in the 3s orbital, so therefore we will not show any electrons. Okay, and Cl, the chlorine atom now has 8 valence electron. Sorry. So now your chlorine atom has initially has 7 valence electron. Okay, so it has gained 1 electron from sodium, so therefore forming your chloride ion. So therefore now there are 8 valence electron in the chloride ions. Okay, so you see that dot and cross diagram, we represent only the valence electron. So likewise for magnesium oxide, okay, magnesium, 2 valence electron, so we draw the 2 dot to represent the 2 valence electron in magnesium. Oxygen, there are 6 valence electron, so if there are 6 valence electron, we draw the 6 valence electron like that. Okay, so what happened here is magnesium is going to transfer 2 electron to oxygen. So magnesium now with a 2 plus charge because lose 2 electron, so therefore there is no more valence electron in the outermost shell, whereas your oxygen now has 8 valence electron because you gain 2 electron from magnesium. So in this case, there will be a 2 minus charge to show the 2 electron that is gained. Okay? All right. So when we are drawing dot and cross diagram, please make sure that it's only dot and cross. Usually we don't show any other symbols. And please do not show the circle or the shell to show the shell. All right. We are only interested in the valence electron. That means the outermost electron. Okay. Now, let's go on to the structure of ionic compound. Now, just now we talked about metallic structure, right, which is a giant metallic lattice. So now, because the ions in ionic compound, they are of opposite charge, so they will repel ions of the same charge in every direction. So what you have here now is your ionic compound also have a giant ionic lattice structure, but in this case, you have oppositely charged ion arranged in a regular three-dimensional lattice structure. Okay, so what you have here is, we call this structure a giant ionic lattice structure. Okay, so you need to know what is, how do you describe the structure of an ionic compound? So it is called giant ionic lattice structure, where oppositely charged ions are arranged in a regular 3D lattice structure. Okay, so if we look at the structure of sodium chloride, you can see that, all right, that the negatively charged ion and the positively charged ion, they are um, arranged in a regular manner. Okay, so um, they are held together by strong electrostatic forces of attraction, and that is called the ionic bonds. Okay, and the ions are arranged such that you have greatest number of contact between oppositely charged ion without pushing ions of the same charge together. Because if you push the ions of the same charge together, then that will lead to repulsion. Okay, so this arrangement will give you the giant ionic lattice structure. Okay, so now let's take a look at the nature of ionic bonds. Now, likewise, ionic bonds is non-directional, so there is no preferred orientation. Your ion will attract an oppositely charged ion in all directions. Okay, now let's move on to the property now. You will see that actually ionic compound, they also have high melting, high boiling point. Okay, and why is that so? Because when we are talking about melting, you need to break down the ionic lattice. Okay, you need to break down the ionic lattice, and in order for you to break down the ionic lattice, you need to supply heat energy. So you realize that you need energy to overcome the strong ionic bonds. Okay, and ionic bonds are relatively strong, if you remember what I've mentioned in the introduction. So therefore, because there is strong ionic bonds or strong electrostatic forces of attraction between oppositely charged ion, so you will see that many ionic compounds, they are actually solid at room temperature. Okay. Okay, so how do we actually measure the strength of ionic bonds? Now, strength of ionic bonds is actually measured by magnitude of lattice energy. Now, we will cover more on lattice energy when we do chemical energetics later on, okay? But you just know the definition of lattice energy for now. Now, you will see that lattice energy is the energy released when 1 mole of ionic solid is formed from its gaseous ions. Okay, so you will see that lattice energy is energy release. So therefore, you can see that in this case, lattice energy is always exothermic. Okay, therefore, it's always negative. All right, so if you have learned enthalpy change, you will see that exothermic means that the delta H will be negative. So therefore, when we talk about lattice energy, we always use magnitude. All right, so you realize that when we talk about lattice energy, we will always refer to it as magnitude. Okay, so if we look at some examples, so the example of lattice energy of sodium chloride will be negative 788. All right, so let's go back to the definition. So 1 mole of ionic solid form, so 1 mole of sodium chloride solid is formed from its gaseous constituent ion, that is Na plus gaseous and Cl minus gaseous. So this is the definition of lattice energy. Okay, so you can see that in this case, lattice energy is always negative. Okay, now why do we need to talk about lattice energy? We need to talk about lattice energy because we can actually make use of lattice energy to talk about strength of ionic bonds. Okay, so you will see that in this case, the strength of ionic bond is proportional to magnitude of lattice energy, and magnitude of lattice energy is proportional to Q plus times Q minus over R plus R minus. Okay, now what are all these terms? Now Q plus is referring to charge. on cation. Okay, whereas Q minus is referring to charge on an ion. Okay, and R plus plus R minus, R plus would be the radius of cation, whereas R minus is the radius of an ions. Okay, so you will see that the magnitude of lattice energy is proportional to this relationship. Okay, but note that you see that in this case it's related to the charge as well as the radius, but charge is actually a more important factor. Okay, so let's take a look at the charge of the ions. So if you look at the relationship, the more highly charged the ions, you will end up with the Q plus and the Q minus being higher, you will lead to a higher magnitude of lattice energy. Now take note that I always use magnitude, as I've mentioned before, I always use magnitude because lattice energy is always negative. So if I talk about greater lattice energy, it becomes very confusing. So we use magnitude. Okay, can? So if you have a when you have a higher charge of ions, that means the Q plus and Q minus are higher, this will lead to a greater magnitude of lattice energy. So when there's a greater magnitude of lattice energy, that means the ionic bonds will be stronger. Okay, the next factor here is the size of the ions. So if you look at the size, again, let's go back to the relationship. That means, let me write down the relationship. So magnitude of lattice energy is Q plus Q minus over R plus plus R minus. So therefore, the size of the ions, so if you will see, if the size of the ions are smaller, all right, your R plus, R minus are smaller, the magnitude of lattice energy will be bigger. So when the magnitude of lattice energy is bigger, that means your ionic bonds will be stronger. Okay, so whenever you are asked to compare strength of ionic bonds, you go back to magnitude of lattice energy, and from there, magnitude of lattice energy is proportional to Q plus Q minus over R plus plus R minus. This relationship you should know. Okay, can? So let's take a look at the quick check. So quick check, you are supposed to explain which one has a stronger ionic bonds. So you know that when we are talking about stronger ionic bonds, I should talk about, that means they are talking about strength of ionic bonds, I should talk about magnitude of lattice energy, and magnitude of lattice energy is Q plus Q minus over R plus plus R minus. So first thing, write down this relationship first. Okay, so you will see that in this case, sodium fluoride is NaF, right? So it's talking about the cation being Na plus, and ion being F minus. Sodium chloride would be Na plus and Cl minus. Correct? So now, if we were to compare the two ionic compounds, first of all, you see that both compounds, they have the same cation. Both Na plus cations are the same. Okay? And you will see that the magnitude of the charges of all the ions in NaF and NaCl are the same. What do I mean by that? That means if Na plus is the same, the charge will be the same, right? But the charge on F minus and Cl minus are also the same. That means they are all minus one charge. So the magnitude of the charge will be the same. So that means in this case, Q plus and Q minus are the same now. Now, R plus will be the same because it's the same cation. So therefore, we will compare only the R minus, which is the radius of the anion. So you will see that between Cl minus and F minus is a smaller anion. So if F minus is a smaller anion, all right, the magnitude of lattice energy will be higher. So if magnitude of lattice energy is higher, that means NaF will have a stronger ionic bonds. Okay, can? Now let's move on to the next part. Okay, same thing. Again, we are talking about which one having a stronger ionic bonds. So if that one has a stronger ionic bond, we should always talk about magnitude of lattice energy. All right. So write down the relationship first. Then let's consider the different ions that's inside there. So you have Ca, 2 plus, and F minus. This is Na plus and F minus. Correct? So first thing, identify in this case, both the ions are the same. Both anions are the same. That means your F minus. Both have the same anion, so I can disregard Q minus, R minus. Okay, so now you will see that in this case, the cation is different. All right, what is different? Ca2 plus compared to Na plus. So the charge, the Q plus is different. So the charge on Ca2 plus is larger than that of Na plus. Okay, but on the other hand, okay, you will see that Ca2 plus, the size is larger than Na plus. Now, go to your periodic table, you will see that Na is in period 3, whereas calcium is in period 4. So you will see that um, those in period 4 has an extra quantum shell, so therefore the size will be bigger, right? So Ca2 plus will be, in terms of ionic radius, it will be larger than Na plus. So therefore now you have two contradicting factor. So Ca2 plus has a higher charge, but it also has a higher radius. So in that case, we have to tell me that which one is more important. So in this case, you need to tell me that charge has a greater impact. So charge is a more important factor here. So if charge is a more important factor, then you will see that the magnitude of lattice energy for calcium fluoride will be larger than the magnitude of lattice energy of sodium fluoride. So because of that, your calcium fluoride will have stronger ionic bonds. So take note that you will need to consider all the factors. Okay, so given in this example, your Ca2 plus, although the charge is higher, but the size is also higher. So you end up with contradicting uh, factors that will affect your magnitude of lattice energy. So in this case, you need to tell me that charge is of a is of a more important factor, or charge has a greater impact. Okay, so that's the part on strength of ionic bonds. Okay, so next we will go on to the next property on ionic compound. Now, ionic compounds, they are readily soluble in polar solvent, but they are insoluble in non-polar solvent. So one example of a polar solvent is actually water. Okay, but first of all, we need to understand why is water considered polar. Now, this is just a simple explanation. When we go on to covalent bond, when we talk about polarity, bond polarity and polarity of molecules, this will be covered in greater details. But I need to explain to you why do we consider water to be a polar solvent. Now, water, okay, water is oxygen bonded to hydrogen. Okay, now so there is a covalent bond formed between oxygen and hydrogen. Now remember we talked about electronegativity. So electronegativity is the electron pulling power, right? So in terms of electronegativity, oxygen is actually more electronegative than hydrogen. So if oxygen is more electronegative, that means oxygen has a higher electron pulling power, so it's likely to pull the bonded pair of electrons closer to itself. So if the bonded pair of electrons is closer to oxygen, oxygen is going to acquire a delta minus charge, whereas hydrogen will acquire a delta positive charge. Now, this delta negative and delta positive, these are partial charges. That means they are not, it's not like ionic compounds where you transfer the electron. Okay, so they are not full charge. Okay, so you will see that we will consider water to be polar because there is uneven distribution of electrons in the molecule, such that the oxygen is partially negative, whereas hydrogen is partially positive. So that is why water is polar. Now, if we look at the solubility, now in order for your ionic compound to dissolve, you need to break down the ionic lattice. Okay, and in order for this lattice to be broken down, you need to supply it with energy. Okay, so where will this energy come from? This energy will come from the solvation or hydration if the solvent is water. So this energy is going to come about from the solvation of the ions. Okay, now what does it mean by solvation? You can look at the video. All right, so let's take a look at the video to see what is the process of solvation?
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Okay, so you can see that because water is a polar solvent, so there is delta minus and delta positive charge on water molecule. So wait, let me just show you. Okay, so this is one molecule of water. So oxygen has a delta minus charge and hydrogen has a delta positive charge. So what happened here is the oxygen end, which is delta negative, is going to be attracted to the cation, all right, the positively charged cation. Okay, and in that case, it forms the ion dipole interaction. Now, what does it mean by ion dipole interaction? That means it's the interaction that occurs between the ions and water molecule, which is a dipole. So this ion dipole interaction is going to release energy. Okay, likewise, for another water molecule, all right, it's going to form ion dipole interaction with the delta positive end of the hydrogen being attracted, all right, to the negatively charged anion. So they form ion dipole interaction. And you know that when interactions are formed or when such interactions are formed, it actually releases energy. Okay, so therefore, this energy is going to be used to break down the ionic lattice structure. Okay, so when these ions are completely solvated, that means you form the ion dipole interaction. This interaction is going to release energy, and this energy is used to break down the lattice. So if the energy is sufficient to break down the lattice, then the ionic solid will dissolve. Okay, so this is basically what I've explained. So in order for ionic compound to dissolve, you must first break down the ionic lattice, and this requires energy. So where is this energy going to come from? This energy is going to come from release of energy that's caused by solvation. All right, and what happens during solvation? The solvation happens when you have the ions surrounding, rather the solvent surrounding the uh, ions, and how do they surround the ions? They form ion dipole interaction, and such interaction, when you form such interaction, it actually releases energy. So when enough sufficient energy is released, is enough to break down the lattice, the solid will dissolve. Okay, now there are some ionic compound that will not dissolve. Sorry, there are some ionic compounds that will not dissolve in water. Okay, that is because the ion dipole interaction did not release enough energy to break down the lattice. Okay, so on the other hand, your ionic compound will not dissolve in nonpolar solvent because you is unable to form ion dipole interaction, and the ion solvent interactions releases lesser energy that is needed to break down the lattice. Okay, so like what I've mentioned, not all ionic compounds, they are soluble in water. So your aluminum oxide and silver chloride, they are generally insoluble, although they are ionic. So the reason is because the energy that's released when forming the ion dipole interaction is not enough to overcome the energy that is needed to break down the ionic lattice. Okay, now the next property here would be ionic compounds. They are actually good conductors of electricity in molten and aqueous state because of the fact that in molten and aqueous state, all right, your ionic lattice will break down to give you your mobile ions. Okay, so the ions that we have here, all right, they are mobile now because in molten and aqueous state, and these mobile ions, because they are charged, they can act as charge carrier when a potential difference is applied. Okay, now take note that ionic compounds, they are unable to conduct electricity in solid state because in solid state the ions are actually fixed in the lattice structure. So when they are fixed in the lattice structure, they are not mobile, so they cannot act as charge carrier when the potential difference is applied. Okay, now the last property of ionic compound is they are hard and brittle. Okay, now you know that the ions, they are held by ionic bonds in a ionic lattice structure. So therefore, when you have a force applied, there will be the ions, the layer of ions will have a slight displacement. So when that happens, you will see that ions of the same charge, all right, they are brought together. So when they are together, they will repel. So when they repel, you actually force the crystal apart. Okay, so there is a diagram showing you what happened. So when you have a force applied, you actually um, the positive and negative, they are no longer aligned. So therefore, you end up having ions of the same charge being brought together. And when you have the ions of the same charge being brought together, there is repulsion. So when there's repulsion, this will break your crystal apart. So there will be causing it to be brittle. Okay,